Hello everyone! Today we're going to be introducing the concept of intermolecular forces. Specifically, we'll be looking at a type of intermolecular force known as London dispersion forces and seeing what factors contribute toward London dispersion forces in molecules. We'll also see how temperature and intermolecular forces work together to influence what phase of matter molecules will manifest themselves in. First, let's explore the difference between intramolecular forces and intermolecular forces. Intramolecular forces are interactions that hold together atoms within a molecule, i.e., covalent bonds. Intermolecular forces, on the other hand, are attractive forces between separate molecules. These interactions are generally much weaker than intramolecular forces like the covalent bonds holding together molecules. To understand how these interactions work, it's important to relate them back to energy. Breaking bonds or interactions, be them intramolecular forces or intermolecular forces, requires, aka absorbs, energy. These are endothermic processes. Forming bonds or interactions, on the other hand, releases energy and is therefore an exothermic process. Matter is commonly found in three different phases on Earth. Here we have water, H2O, in three phases. We have the solid iceberg floating in the liquid water, and in our atmosphere we have the gas form of water. But what dictates what form of matter molecules will take on? Let's explore that right now. In order to explore this, we're going to need to invoke something called kinetic molecular theory, which basically looks at the movement of molecules at a really small level. Essentially, phase is a battle between intermolecular forces and kinetic energy. Let's take a closer look. As you're probably familiar, if you've ever frozen water to create ice or boiled water, temperature affects the phase of matter that we observe. Temperature is, in effect, a macroscopic manifestation of molecular motion. We'll explore it more thoroughly as we talk about kinetic molecular theory later on. But for right now, let's talk about how temperature and intermolecular forces affect the phase of matter. With solids, the kinetic energy of the molecules is less than the intermolecular forces holding together the molecules. Solids are known for having a fixed shape. Why is that? It's because the particles are held in place by their intermolecular forces. Unless it's at 0 Kelvin, absolute zero, these particles, these molecules still have kinetic energy, but it's not enough to overcome the intermolecular forces that hold them together. With a liquid, on the other hand, the kinetic energy is about equal to the intermolecular forces. This means that the molecules will be held together to some extent, but they have enough energy to slide past each other. With gases, however, the kinetic energy of the particles is greater than the intermolecular forces. With gases, the molecules are moving too fast to be constrained by their intermolecular forces. So we end up with rogue particles. So if we compare the relative kinetic energy of a substance in its solid versus liquid versus gas phase, the solid has the least kinetic energy, whereas the gas has the greatest. Since temperature is a macroscopic manifestation of the kinetic energy of molecules, the trend for temperature of solids versus liquids versus gases is the same. To relate this back to our familiar example, ice is cold. If we're boiling water and turning it from a liquid to a gas, boiling water is hot. Melting points, aka the temperatures where molecules turn from a solid into a liquid, and boiling points, the temperatures where molecules turn from a liquid to a gas, are actually reflections of the intermolecular forces. To go back to our familiar example, the melting point of ice is 0 degrees Celsius. The boiling point of water, where it goes from a liquid to a gas, is 100 degrees Celsius. As it turns out, the melting point and boiling points of substances are actually pretty good reflections of their intermolecular forces. The more intermolecular forces something has holding it together, the more energy in the form of heat it's going to take to turn it from a solid to a liquid or a liquid to a gas. So more IMFs means more interactions holding molecules together. Ergo, it will take more heat to melt or boil a substance. As a result, a substance's melting point and boiling point are good gauges of the intermolecular forces holding together that substance. As a summary of the past few slides, remember that intramolecular forces are the forces within the molecule, the covalent bonds that are holding together the molecule or compound. The intermolecular forces, on the other hand, are the interactions between different molecules. So, an example that I like to think about is intramurals are sporting events, competitions held within a given institution, like a university. An international flight is a flight between two different countries. And remember that intramolecular forces are stronger than their intermolecular forces counterparts. It's the intramolecular forces that define what compound we're looking at, and it's the intermolecular forces that dictate if we're going to have that compound as a solid or a liquid or a gas at different temperatures. Regardless of if we're looking at intra or intermolecular forces, breaking bonds and interactions always costs energy, whereas forming bonds or interactions always releases energy. A good example of this is how we sweat to cool ourselves down. So sweat, liquid water on our skin, in order to evaporate it, it requires energy. Where does that energy come from? Well, it takes heat from our body to evaporate it, therefore cooling us down. Now, let's delve in deeper and look at a specific type of intermolecular force known as London Dispersion Forces. What are London Dispersion Forces? Well, London Dispersion Forces are attractive forces that act between all molecules, and they're the result of the formation of instantaneous and induced dipoles. So by virtue of being a molecule, a given substance has the capacity to form these interactions, these London Dispersion Forces. Now, what are instantaneous and induced dipoles? Let's take a closer look using two different noble gases, helium and neon. As we know, electrons don't move in a perfect orbit, but these cartoons will be useful for us getting to the root of what an instantaneous and induced dipole is. So imagine that we have these electrons that are just moving randomly about helium. These electrons may be randomly distributed on opposite sides of their respective orbital. Now, what would happen though if they happen to move more toward the same side? So instead of being well distributed like they are in our first example, what if they are something like this? Where now our electrons are more so gathered on the same side of this particular orbital. This would create, albeit temporarily, an electron-rich side of our atom, which would then have a partial negative charge, and consequently, an electron-deficient side of our atom, which would also consequently have a partial positive charge. Now, because this is from the random movement of the electrons, this is only going to be temporary. Hence, an instantaneous dipole is created. So imagine now that this partial negative end of a helium interacts with another helium with its two electrons. What's going to happen to those two electrons if there is a negative electrostatic charge interacting with them? Are they going to flock toward it, over here, or away from it, over there. You got it! They're going to tend to move away from that negative charge, because we know negative charges repel negative charges. So what does this do to our second helium here? It now induces a partial negative side of our helium, and consequently, a partial positive side of that helium as well. This is what's called an induced dipole, because the dipole from the other helium created this temporary, albeit dipole. What do we know about negative and positive charges and how they interact with each other? That's right, they attract each other. Whoop, 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 whoop. But what if we have something that has more electrons? So, for example, let's look at neon. Whereas helium only has 2 electrons, neon has 10. What implications does that have on the ability of neon to form temporary dipoles? So again, let's use an oversimplifying cartoon to illustrate the effect of more electrons here. So with neon, with its 10 electrons, they can also distribute themselves randomly to create a temporary dipole. Pow! Kabloomers! Now, with more electron density, what would that do to a relative partial positive versus partial negative? Well, now, in this case, we have a much more electron-rich side, leading to a partial negative side that's greater in magnitude than our helium counterpart. Consequently, we would also have a greater partial positive charge on the other side of our neon. How would this instantaneous dipole affect another neon? Well, let's just make this cartoon a little bit smaller so that we have room to illustrate this point. It would in turn have a greater influence on the relative electron distribution of another neighboring neon, therefore creating a more prominent induced dipole, therefore creating an even greater attraction between the partial negative and partial positive sides of this atom. So the effect of more electrons is, in effect, it increases the potential for greater instantaneous and induced dipoles, therefore more London dispersion forces. So let's continue to work with this idea. As said before, electrons are in constant motion, and this can create temporary dipoles. Remember, these instantaneous temporary dipole moments are formed when the electron density is greater on one side of an atom or molecule, therefore creating an electron-rich partial negative end and an electron-poor or deficient partial positive end. And remember, these dipoles can then interact with other molecules to further induce another dipole. So, as a result, we have these induced dipole interactions. Now, these interactions are not permanent. If we were to remove these molecules, the electrons back in their random motion would create, again, a random distribution of the electrons that could make one end partial positive or negative. Therefore, these are temporary dipoles. As we saw before, a larger atom like neon has more capacity, well, larger with respect to helium, has more of a capacity to create a more electron-rich and poor side, creating a greater partial dipole. So, as a result, London dispersion forces are dependent on the polarizability of an atom or molecule. What is polarizability? Well, polarizability, denoted by alpha, is the ease with which the electron cloud of an atom or molecule is distorted by an outside influence, thereby inducing a dipole moment. And what factors contribute to the polarizability of a molecule? How can we increase the polarizability of a molecule? Generally speaking, the 2 key factors are a greater mass, therefore more electrons, and more available contact space. We'll take a closer look at that in just a moment. But to go back to the greater mass, think again about helium and neon. Which one is more polarizable? Well, the neon has a greater mass, it has more electrons, therefore can create a more pronounced temporary dipole. This example with atoms also works itself into molecules. Generally speaking, larger molecules have the capacity to create more London dispersion forces with other molecules. So with that in mind, let's compare these two alkanes, propane and octane. Given what we just talked about, which of these do you think would take more heat in order to disrupt the intermolecular forces? A, propane with 3 carbons, or B, octane with 8 carbons? Take a moment and decide. Dun 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 dun. See, it's kind of like a clicker question. Dun 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 dun. If we consider the relative masses and number of electrons in propane versus octane, which one's the more polarizable molecule? The C8H18 is more polarizable. It's got the greater mass. Therefore, when compared to the ability for C3H8 to form London dispersion forces, there are considerably more opportunities for octane. And when you think about this in real life, propane at standard pressure exists as a gas. It's oftentimes used to fuel grills, for example. Whereas octane is the main component in gasoline, which famously is a liquid at standard temperature and pressure. And to confer, let's use some data here. So what are the boiling points of these respective species? Propane's boiling point is a tepid -42 degrees Celsius. That's a pretty cold boiling point. So, at most temperatures that we're familiar with, existing in, propane is going to be a gas. Octane, on the other hand, has a boiling point of 125.6 degrees Celsius, considerably higher. In fact, that's greater than the boiling point of water. So, we can see here that these molecules, due to their respective London dispersion forces, that has a notable impact on the phase of matter at a given temperature. In fact, while we're on the topic, let's look at 5 different hydrocarbons: methane, ethane, propane, butane, pentane. So, considering what we just talked about, which has the highest boiling point? Choose. Bum 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 bum. That's right, it's going to be pentane. Let's throw some data up here for each of these boiling points. Look at that trend. Methane, with its 1 carbon and 4 hydrogens, is negative 165 degrees Celsius. Ethane is negative 89 degrees Celsius. Propane is negative 42 degrees Celsius. Butane is negative 1 degree Celsius. And pentane is 36.1 degrees Celsius. This trend, it works! So generally speaking, the greater the molecular mass, the greater the intermolecular forces, and therefore, the greater the melting point and boiling point. And I want to emphasize this is generally speaking. How that mass is distributed in the molecule, and also other factors such as dipoles, permanent dipoles within the molecule, and an ability to do something called hydrogen bonding will also make an impact. We'll explore dipole-dipole interactions at another point, and hydrogen bonding in a subsequent lecture. For right now, though, let's look at how the mass is distributed in the molecule and how the shape actually impacts the London dispersion forces. To do that, let's consider these two molecules, N-pentane and neopentane. Now, both of these have the same formula of C5H12. They are constitutional isomers of each other. Now, it turns out, though, that these have different physical properties, including the melting point and boiling point. So which of these two molecules, N-pentane, which is splayed out in a more linear fashion, or neopentane, which is a more compact molecule, would you expect is able to create more interactions with fellow molecules of their type? Take a moment and choose which one you think would have the higher boiling point. Da-na-na-na, okay, etc., etc., etc. So, the boiling point of N-pentane is 36.2 degrees Celsius. What then is the boiling point of neopentane? Drum roll! 9.5 degrees Celsius, considerably lower than N-pentane. Now that's interesting. It's the same formula, but one has a considerably higher boiling point. Why is that? Well, if we consider the shape, which one has more of an opportunity to interact with other molecules? N-pentane, with its linear shape like that, can actually stack nicely with other N-pentanes, therefore having more interactions and enjoying more intermolecular forces than neopentane as a counterpart. So this one, and this is obviously a 2D depiction of this, but if we can picture what would happen if we have these molecules interacting, there's less surface area that they're able to contact to interact through their intermolecular forces. So more surface area contact leads to greater London dispersion forces. We can see that there's considerably more in the N-pentane than there is with the neopentane. To put it succinctly, more surface area means more dispersion forces. There's more opportunity for them to interact. And two examples that sort of illustrate this are, if you think of Velcro, if you have two Velcro balls, they're not going to attach to each other very readily. You can easily pull them apart. But if you have two Velcro strips and you try pulling them apart, it's going to take more effort to... That's the sound that it makes when you pull it apart. Pull them apart. So here we have an illustration of the considerable more interactions of N-pentane compared to neopentane, where there's less surface area contact and therefore fewer interactions. The other example that I like to think of is a more culinary example of spaghetti versus meatballs. Now, this is a gross oversimplification of this because it's not like these molecules are actually physically tangling. But if you consider spaghetti versus meatballs, which one are harder to pull apart from themselves? Spaghetti or meatballs? Well, meatballs, they can't really tangle with each other. Based on their spherical shape, they're pretty easy to pull apart. But spaghetti, on the other hand, based on its long shape, can easily tangle with other spaghettis, and then you get a spaghetti knot that's very difficult to pull apart. So which one's harder to pull apart? Spaghetti. And if you consider back to pentane, N-pentane versus neopentane, N-pentane is like the spaghetti, more interactions, more energy to pull apart, whereas neopentane are the meatballs of the pentane world. They're not getting as tangled. Again, a gross oversimplification, but one that works pretty well for picturing this with a familiar example. To invoke one more familiar example, something that we might be able to relate to on the macroscopic level, let's revisit London dispersion forces and talk about some interesting nutrition correlations here. So here we have the primary components of several spreads and oils. So butter has a decent amount of stearic acid or palmitic acid, and it should be noted these when you find them in actual like olive oil and butter, etc., they're generally grouped together in what are called triglycerides. But let's just look at these individual units of fatty acids. And let's consider what we know about the properties of butter, olive oil, and margarine. Which one tends to be a solid at room temperature versus a liquid at room temperature versus a kind of whatever margarine is at room temperature? So stearic acid has an 18 carbon chain in it. This 18 carbon chain can stack nicely with other stearic acids. And we'll add the carboxylic acid functional group at the end here. So as a result, there's a lot of opportunity for interaction between these, which creates a greater melting point. So we have our 18 carbon chain here, and the melting point is 69 degrees Celsius. Okay, well, how does that compare to palmitic acid, also prevalent in butter? Palmitic acid is a very similar molecule, except it only has a 16 carbon chain. So there's still lots of opportunity for interactions between separate molecules of palmitic acid. But would you predict that this has greater or fewer intermolecular forces when compared to stearic acid? Well, let's consult the melting point. So quickly make a guess, and the melting point of palmitic acid is 63 degrees Celsius. Very similar in terms of shape, but because it's got fewer carbons and less mass, there's less opportunity for the London dispersion forces. Now, so these are looking at saturated fats. What if we have an unsaturated fat where we have double bonds inside of our molecules. Turns out that those influence the shape and properties of these molecules. So oleic acid is the alkene equivalent of stearic acid, so it has here this double bond here, which actually serves as adding a kink to the molecule. So as a result, it can't stack as well. It still has that 18 carbon chain, but let's see how its melting point compares to stearic acid. It's only 14 degrees Celsius. Very, very interesting. And, olive oil, if you're looking at olive oil at room temperature, well, hopefully it is a liquid, as are, oils. So that's the story with our cis fat found in olive oil. What about a trans fat, like what's found in margarine? Oops, sorry, this should be margarine, not margarine. My apologies for my typo here. Oleic acid, which can be found in margarine, also has an 18 carbon chain, but in this case we're looking at a trans fat. And we have a double bond here, which makes the molecule more rigid, and it turns out that rigidity actually ends up influencing the melting point. So this one has a melting point that's somewhere in between that of oleic acid and stearic acid. And it has a melting point of 45 degrees Celsius. And, margarine has a melting point somewhere in between that of butter and olive oil. And it sort of has, a different texture as a result of its physical properties. And as one final note for this unit, ions and permanent dipoles can induce dipole moments in nonpolar species. So let's just take, for example, what if we have hydrogen gas, H2, interacting with, say, sodium plus, the cation? What would we expect that sodium plus cation to do to the electron density in hydrogen? Well, it's going to be able to induce a temporary dipole. So this positive charge of sodium is going to be able to draw the electron density of hydrogen closer to it, therefore creating this interaction here. That is known as an ion-induced dipole interaction because we have an ion, sodium, inducing a dipole in in this case, hydrogen. Another interaction is called a dipole-induced dipole interaction, and it's exactly what it sounds like. It's when a dipole, a permanent dipole in a molecule, induces a temporary dipole in another molecule. So let's also look at hydrogen this time, H2, but consider what it would do if we interacted it with, say, water, H2O. So water, as we know, has a bent shape, and one of the important properties of water is that it has a partial positive end and a partial negative end. The partial negative end would drive away the electron density in hydrogen, H2. So as we can see here, what it's doing is basically pushing the electron density in hydrogen over to the other side. This is creating a temporary dipole. So again, this is called a dipole-induced dipole interaction because water has a permanent dipole based on the electronegativity difference of oxygen and hydrogen and the bent shape of the molecule. Whereas in this case, what it's doing to hydrogen is creating a temporary induced dipole. So it will be present, it will allow the hydrogen and the water to interact with each other, but if we remove the water, then the electrons are going back into their random motion, which would remove this dipole that was induced. And that concludes our introduction to intermolecular forces and our discussion on London dispersion forces. Thank you very much for your time and have a wonderful day.